In this video, we will learn how to solve a system of two linear equations in three variables. When talking about solving linear equations, it's important to note the three different types of solutions and their corresponding outcomes. The first type of solution is the independent solution. In this case, the lines will have different slopes and therefore intersect only once. Since these lines only intersect once, there is only one solution to this type of system. The second type of solution is the dependent solution. The lines defined in this system of equations will coincide, meaning they have the same slope and the same y-intercept. This gives us infinitely many solutions. The third and final type of solution is an inconsistent solution. Here the lines have the same slope but have different y-intercepts, making them parallel lines. This type of system does not have a solution. We can solve systems of two linear equations in two variables, as well as systems of three linear equations in three variables. But what happens if we have a system of two linear equations in three variables? In this case, the two linear equations will always correspond to two planes in three dimensions. As a result of this, our only possibilities are no solution, meaning the planes are parallel, or infinitely many solutions, meaning the planes intersect in a line and the points on that line are the solutions. Let's do an example where we solve a system of two linear equations in three variables. We are given the equations 3x plus 2y minus z equals 4 and x minus 4y plus z equals 12. To keep track of them, let's label the first equation 1 and the second equation 2. First, we want to see if any of the expressions will cancel out when we add the equations together. We can see here that we have a negative z in equation 1 and a positive z in equation 2. So we'll add the equations together to cancel out the z term from each. This gives us 3x plus 2y minus z equals 4 plus x minus 4y plus z equals 12. The z terms cancel, giving us 4x minus 2y equals 16. Therefore, equation 1 and equation 2 are both true if 4x minus 2y equals 16. Since we know there is a solution, we know the solution has to be a line. From here, we can't solve for either variable numerically, so we'll use a parametric representation. Let y equal a, where a can be any real number. Now we can solve for x in terms of a. So we have 4x minus 2a equals 16. Add 2a to both sides to get 4x equals 16 plus 2a. Solving for x, we get 4 plus 1/2 a. Now that we've found x and y, we can find z. So far, we have x equals 4 plus 1/2 a and y equals a. Substitute these expressions into equation 2 to find z. This gives us 4 plus 1/2 a minus 4a plus z equals 12. Subtract 4 from both sides and combine the a terms to get negative 7/2 a plus z equals 8. Finally, add 7/2 a to both sides to get z equals 8 plus 7/2 a. Now that we've solved for all three variables, we can write the solution. The solution is the line in three dimensions given by 4 plus 1/2 a, 8 plus 7/2 a, where a is any real number. As an added note, we can say that any real number a corresponds to a point on the line of intersection.